Good afternoon. I currently work for a company called Daines as a building physicist, and I'm going to talk to you about condensation simulation in a swimming pool environment, which I've done some work on recently. Predicting condensation risk in swimming pools is a challenging experience because they are an inherently risky environment for condensation. Condensation is a problem because of it causing fabric damage, mould, and there being a safety risk associated with it. And it's caused by warm, moist air coming in contact with cold, which reduces the saturation vapor pressure of the air and causes condensation. So in a swimming pool environment where you've got warm, moist environments adjacent to cold, conditioned environments, it's inherently quite risky. So the big question is how warm and how moist. So I used building simulation modelling and HVAC to predict the room temperatures and room humidities. So this captured latent gains and the latent impact of cooling cycles and air recirculation through air handling unit chilling, dehumidification impacts. This was used to predict the room temperature and room relative humidity, which were then used as inputs into my condensation modelling later in the process. So this allowed me to calculate the critical surface temperature for the avoidance of mould growth, condensation and other related damage. The second input that was needed was external conditions, because external conditions are often the cold location within the project. And luckily we've got good data available to us produced by CIBSE for external weather conditions. However, I did need to do some processes to it to convert it from typical weather to climate change scenarios or to extreme weather scenarios to ensure that we got an accurate assessment. This enabled us to carry out surface condensation assessment. So I used numerical modelling to assess the risk of surface condensation in thermal bridging within the projects. So the model on the left is two internal rooms separated by an internal wall meeting an external wall at ground level. And this shows the temperature on the internal surfaces, and on the right it's been tuned to show where it is too cold and there is a risk of mould growth. So there is a risk of mould growth growing in the corners of the ground floor rooms, currently as modelled. I additionally used this to predict interstitial condensation by using a vapor diffusion numerical model, which looks at vapor diffusing through the materials and looks at the saturated vapor pressure within the materials. This is basically a 3D version of a simple glacier diagram and enabled me to estimate the risk of condensation forming within build-ups. So we did this, we iterated, we got answers and we predicted condensation risk. So in summary, I feel like this is a novel methodology that I've not seen anyone else doing. This integrated approach of taking the entire building design and using the entire building design to pull together the input conditions to go into a good thermal model, which could be used for a number of things, so operational energy, thermal comfort, and then the prediction of internal room conditions, coupled with the extreme weather scenarios produced by CIBSE and the climate change weather scenarios produced by CIBSE. We pull this all into finite difference numerical modelling to give us a condensation risk. And the really strong thing about this approach is it allows us to address both architectural risks and mechanical risks. So we don't have to just put more insulation in to make the problem go away. We can also look at the mechanical design to make the problem go away. So by rerouting ventilation flows through the building or controlling the humidity in the building, we could control condensation risk. In this particular project, we controlled condensation risk through a number of factors, one of which was more insulation in the foundations, the other was better control of plant rooms. So plant rooms were inside the internal envelope, that by identifying a risk using this, we were able to slightly modify farm room design that allowed us to eliminate risk in design. Thank you very much.
My first two-fold question. First one is, where do you get your thresholds to assess condensation risk? Because I know that...
Sorry, I really can't hear you.
How do you get your thresholds to assess condensation risk? Because there's not specific guidance for swimming pools in the UK. And the second part of the question is, if you are thinking to capture the dynamic profiles of moisture, what find different models are static models.
Okay, so the methodology that was used was I followed the guidance in BSEN ISO 13788, which allowed me to calculate surface condensation risk, and I used that to work out surface condensation risk. All of the dynamic modelling was used to work out at monthly averages, and the monthly averages were used in the condensation model. So there was a conversion between a fully dynamic model to a more static methodology, but the data inputs to the static methodology came from the dynamic model.
Thank you.